So this is Discrete Maths, Maths 1081, and we're having a look at a selection of problems from Chapter 4, which is a chapter on combinatorial mathematics. I've chosen to do, for this particular example, I've chosen quite a hard one. This is question 26. It's marked with a star, so it's a slightly more difficult problem if you haven't seen it before, seen the ideas of it. So I'm going to be using this basic fact that you would have learnt earlier in lectures and used in earlier of the tutorial problems. It says if you're looking at this equation here where the xi's, all of these x's, are from the natural numbers, that means they can be positive integers or zero, so we're allowed to include zero. Then if I fix m and n, then the number of solutions of this is given by this binomial coefficient. I just remember it as m plus n minus 1, choose m minus 1. There are other ways of writing it. You can use some of the properties of the binomial coefficients to write this in a slightly different way, but that's how I like to write it. So that's an established fact that you will have seen in lectures and you'll have used it in earlier problems. So in this problem, we're asked to count the number of solutions of this equation where not equal to n, but less or equal to n. And again, the xi's are allowed to be natural numbers, so some of them could be zero. And what I'm going to do is I'm going to solve this problem, in fact, in two different ways. And that will mean then that I can equate the two answers and I'll end up with a very nice identity, which is what we're asked to prove in the problem. And we can then interpret that in terms of Pascal's triangle, which is a nice thing to do at the end. So what am I going to do with this? Well, one bare hands way of attacking this is to say, well, just think of n being 0, 1, 2, 3, all the way up to n. So replace the right-hand side, put this as an equal, and then just check all the numbers from 0 up to n. So the number of solutions is going to be the number of solutions to x1 plus xr equals, say, k, where I take k to equal 0, 1, 2, all the way up to n. And I'm just going to add them all up. So I'm replacing the lesser equal to with a k, and then I just put k to be 0 up to n, and that'll give me all the solutions for that less or equal to n. So the number of solutions then is going to be, if I put, I'm replacing now the m with r in the formula and the n with k. So if I put k to be 0 in, I'm going to get an r minus 1, choose r minus 1. So there I'm putting k to be 0, and n is k, and the m is r into the formula. The next one, if I now put this to be 1, then I'm going to get 1 plus r minus 1, which will be r, choose r minus 1. And then I will get r plus 1, choose r minus 1, plus all the way up to, when I eventually get to n here, I'll get n plus r minus 1, choose r minus 1. So that's the number of solutions using this sort of bare hands approach of simply replacing n with all the numbers from 0 up to n and replacing the less than or equal to with an equal sign. Now another way of thinking about it, here's an alternate way of thinking about it that will also give me what appears to be a different looking formula, which will be a simplification of this, and I can equate the two. Another way of thinking about it is the following. When I'm doing problems like this, I like to imagine them quite graphically. So I imagine that I've got n marbles and I've got r urns. So I've got a number of urns in front of me and I've got n marbles, and I'm going to toss the marbles into the urns. So up here I've got m urns and n marbles. And we know what the formula is in this particular case. So all I'm going to do, when I want less or equal to n, all I'm going to do is I'm going to add in an extra urn. and then I can toss my n marbles into all of those urns, and then at the end just ignore the final urn that we added in, and then we'll get less or equal to. So writing that down, I can also simply solve x1 plus x2 plus up to xr plus add in an extra urn, which I'll just call y, and make that equal to n. So I'm saying if this is less or equal to n, then this plus something equals n. I can get rid of the less or equal to, replace it with an equals, and then I just simply ignore that last urn at the end, and I've got my number of solutions. So all that's going to do is, when I go to apply the formula, this has, so remember I'll have r plus 1, I'll have r plus 1 urns now, so it's n plus r plus 1, subtract 1, and then I'll have r plus 1 urns, and I subtract 1. That's what the formula here tells me to do. You subtract 1 off the number of urns. And when that simplifies, you get n plus r, choose r. And I think that's the formula that we were asked to get. And so now I can equate those two. So equating them, I now have a nice combinatorial identity on the binomial coefficients. So I have r minus 1, choose r minus 1, r, choose r minus 1, plus all the way up to n plus r minus 1, choose r minus 1. That must now equal what we got here, which is n plus r, choose r. And there is the formula achieved. I want to now interpret this in terms of Pascal's triangle. So let me draw up a little Pascal's triangle and interpret this and show you what this means when I specialise this down to some rows and columns in Pascal's triangle. So Pascal's triangle looks like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And you can keep going, but that's enough to be able to see what the pattern is. So in particular, I'm going to specialise here. I'm going to put r equal to, say, 2 and n equals 3 into my formula here. I think that's what I'm going to do. So I will do 0, 1, 2. No, I'm going to put actually I'm just going to put 3 here and 2 there, I think. So I see what's happening. So looking across to here, if I look to the first binomial coefficient, that's 2 choose 2. So 2 choose 2 is that one. The next one then is going to be 3 choose 2. So that's the fourth row down, and you go 3 across. So that's that number. And as I keep summing across here, then I'm going to be moving down the triangle, but counting across the same numbers. So I go 0, 1, 2, 0, 1, 2, 0, 1, 2, and I may as well stop at that point. And now it says that's the same as if I go to the 5th row, but go across one. So 0, 1, 2, 0, 1, 2, 3. And you can see that that works. In other words, if I add up this number plus this number plus this one equals that one. And that's what it says in terms of the triangle. Well, you can do another one as well. Let me choose another colour here. I can do, if I put, say, r equal to 2 and do the same thing, then again I can count here. So I'll get that one, that one, that one, that one, and I add them up, 4, 5, 6, 7, 8, 9, 10, and there it is. There's the 10 down there as well. And so if I add up that one plus that one plus that one equals that one. And that's how you can interpret this combinatorial identity in terms of Pascal's triangle. You just keep moving down a diagonal, and then wherever you like, wherever you stop, the sum's going to equal the number on the other side. There are literally millions of patterns in Pascal's triangle. It is an amazing combinatorial object that people have studied in great detail, and you might like to see if you can find some interesting patterns yourself. All the patterns, there are so many patterns known now that it would be unlikely you would find one that isn't already known, but nonetheless I invite you to play with Pascal's triangle and see if you can find some other interesting patterns there.